bringing the power of IoT to keep streetlights safe and grounded. Here's a video to demonstrate the application of our project. Our project idea is to replace human effort involved in checking of earthing of streetlight through sensor-based system, that is IoT-based earthing system. The general method of checking earthing is done by manually going to each light stations, that is each street light, once in a year or a month, due to which if any problem occurs in street light at any instance, then it can't be detected immediately, which can be dangerous. So to overcome this problem, we resolve whole general checking system to a sensor based system. Three main problems that need to check in earthing system of street light is current leakage, increment of ground resistance, continuity in system. So let's discuss one by one on each problem. For current leakage, we have used a split core current transformer. A split core current transformer operates on the principle of electromagnetic induction. When current flows through the live wire, it creates a magnetic field around the wire. The current transformer, when clamped around the live wire, detects this magnetic field. The current transformer has a core that can be opened and closed, allowing it to be installed without disconnecting the wire. Leakage current occurs when there is an unintended path for current to flow, typically due to insulation failure or damage. In a properly functioning circuit, the current in the live wire should equal the current in the neutral wire. If there is a difference, it indicates leakage. The current transformer measures the current flowing in the live wire. If the total current detected by the current transformer is significantly different from the expected value, which should be 0 in an ideal case, it implies there may be a leakage. The current transformer generates a small alternating current in its secondary winding that is proportional to the current in the live wire. The output is typically low voltage AC signal. The current converter takes the output from the current transformer and converts into a compatible voltage range for the Arduino. The converter output is connected to the one of the analog input pins of on Arduino Uno. The Arduino reads this analog voltage, which is representative of the current flowing through the live wire. The Arduino code continuously reads the analog value, converts it back to a current value using a calibration factor, and compares it to a predefined threshold. If the measured current is higher than the set limit, it means there is a leakage, and appropriate action can be taken, such as activating buzzers and alerts. So for calculating ground resistance, rather using a sensor, we have used a method named as fall of potential method. Fall of potential method is widely used as a technique to measure the resistance of a ground or earthing system. In this, three electrodes are used: earth electrode, potential electrode also known as auxiliary electrode, third current electrode. The current electrode is placed far from the earth electrode, while the potential electrode is placed at the intervals along the line between the ground electrode and current electrode. An AC supply is passed between the ground and the current electrode. The potential electrode measures the voltage drop in the soil caused by the current flowing between the earth electrode and current electrode. Hence, by using Ohm's law, we can calculate the resistance in the ground present. To prove this method, we have practically implemented it, which I will show you now.
In our project, we have measured earth resistance value, and also we are continuously measuring the deviation of earth pit resistance. So we are using here fall of potential method, and here we are practically implemented fall of potential method. We are measuring, taking the readings of voltage, and also we are taking the reading of current flowing in our this circuit, in which we have implemented fall of potential method. Now let's see how we have implemented fall of potential method. First, here we have used earthing rod, which is our main rod, which provide earthing for our electric poles. Secondly, for measuring these readings of voltage and current, we have used another rod, which is auxiliary rod, and we have also used third rod, which is current rod. In between earthing rod and middle one auxiliary rod, we have connected voltmeter to measure voltage in between earthing rod and auxiliary rod. And also we have placed a ammeter to measure current flowing in our whole circuit. By continuously measuring these values of voltage and current and providing it to the Arduino, we are calculating the earth resistance which by Ohm's law, which is resistance of earth bit is equals to voltage reading in between earthing rod and auxiliary rod divided by current flowing in whole circuit. By continuously placing this circuit in our earthing system, we are continuously measuring the earth resistance of our pit, so to provide data to our maintenance team continuously of earth resistance. Also we will place this earthing rod common in between 3 to 4 poles, and this rod will provide earthing to 3 to poles continuously, and earthing resistance of earth will be continuously measured. Now let's see how we are going to measure voltage and current in between. Here we are providing AC power supply to our circuit. We have taken AC power supply from our 220 volt power supply and we have converted that to 18 volt AC supply. Now let's see the readings. Now here we have turned on our AC power supply and here our voltage reading is 1.6 volt, which is in between earthing rod and auxiliary rod, and our current is and here current flowing in our circuit is 65.6 milliampere. Now we will calculate earth resistance by dividing voltage by current, that is 1.6 volts divided by this 65.9 milliampere, and our resistance is coming equal to 24 ohm. From this resistance we will subtract the resistance of this auxiliary rod and current rod. Also we are subtracting the resistance of earthing rod, and then we will get exact value of earth resistance. This all data will be provided to maintenance team continuously by using this follow potential method.
Now for continuity, in this also we haven't used any sensor. We have tried to calibrate it with the fall of potential method. So instead of connecting AC supply direct to the earth electrode, we are connecting it to the earthing wire. So if there is any discontinuity in the earthing wire, then that can be immediately reflected through readings. After this all, the main problem occurs that how we will send this data to the main computer. So for that we are using GSM module and LoRa module. GSM module use cellular network to send messages wirelessly, so it is the best to use in urban areas. While LoRa module use its own network. LoRa module has two parts, LoRa transmitter and LoRa receiver. Transmitter is connected at street light and receiver is to the main computer. So it needs less interference between it. So it is the best to use in rural areas. For this reason, we are using both GSM and LoRa modules. In conclusion, our IoT based streetlight earthing monitoring system represents a significant step forward in ensuring the safety and reliability of urban lighting infrastructure. By continuously monitoring and earthing continuity, this system not only enhances the maintenance process but also minimizes the risk associated with the electrical faults. Through real time data transmission and smart detection, we can proactively address issues, reduce operational cost, and improve overall public safety. This project demonstrates how integrating IoT into everyday systems can lead to smarter, safer, and more efficient urban environments, paving the way for a brighter and more secure future.